Thank you for watching this video. We hope you find it informative. This is an outline of the presentation. In particular, please note sections 5, 6, and 7. There are 3 material or environmental parameters that are important in determining the temperature of a trace, besides the obvious current down the trace. In a board, we have a thermal conductivity coefficient. There are 2 of them. One is through plane, the other is in plane. The in-plane thermal conductivity coefficient is a measure of the conductivity of the heat away from the trace in a plane parallel to the trace. The through-plane conductivity coefficient is a measure of the conductivity through the board perpendicular to the trace from the top layer to the bottom layer. The typical measure of a board thermal conductivity coefficient is between about 0.3 to 0.8 watts per meter per degree Kelvin. By comparison, the thermal conductivity of copper is 385. There are other board material parameters that exist that are related to temperature, but they're really not important for normal board operation. Copper has 3 parameters that are important. The first is resistivity. Recall that resistance is equal to resistivity times the length divided by the conducting cross-sectional area. For electrodeposited or plated copper, which is pure copper, the resistivity is 1.65 microohm centimeters. For rolled copper, which is formulated from an ingot that has impurities, the resistivity is a little higher. We typically think of it in the range of 1.75 microohm centimeters, which is approximately 6% higher than plated copper. If you don't know what kind of copper you have on your board, then you have a 6% uncertainty regarding the resistance of the trace, which translates to a 6% uncertainty in temperature. There is a thermal coefficient of resistivity, which is 0.4% per degree C. That means for a 100-degree change of temperature in the trace, the resistance of the trace will change by 40%. And then finally, there's a thickness variation along a trace. It can be as much as plus or minus 25 to 50%. Now, normally we don't think of thickness variation as being an important variable, but the thickness of a trace is so thin to begin with that any variation along the trace really matters. I will have more to say about thickness variation along a trace later on in the presentation. The third important parameter is the environmental heat transfer coefficient, which we call HTC. This reflects the combined effects of convection and radiation carrying heat away from the board. The typical measure is 10 to 16 watts per meter squared per degree K in normal environments, but quantifying this is really difficult. Physicists know a lot about HTC related to a plate on a surface, but we don't know much about something as small as a trace on a board. This is one area where we need a lot more research. The basic physics behind determining the temperature of a trace is pretty straightforward. The trace heats by I squared R power dissipation along the trace. It cools by conduction of heat away from the trace through the board, both in plane and through plane, and it cools by convection and radiation. A stable temperature is reached when the rate of heating equals the rate of cooling. It's really pretty straightforward. I mentioned earlier that thickness can vary along a trace. This is a 1-inch long microsection along a trace on one of our test boards. And just in this short 40 mil section, we see that the thickness varies from 2.29 mils to 2.60 mils. This is typical all over a board. So, although a stable temperature is reached when the rate of heating equals the rate of cooling, it's really not that simple. Heating and cooling are point concepts. Resistivity is a point concept. Thermal conductivity is a point concept. Thickness is a point concept. Therefore, temperature itself is a point concept. These are thermal images of two different 6-inch long traces. One is 20 mils wide, one is 100 mils wide. We typically think that the temperature is constant along a copper trace, but that is far from the truth. The temperature varies by as much as 1.5 to 2 degrees along the trace, but it even varies from the midpoint of the trace to the edge of the trace, because the edge of the trace cools more efficiently than does the midpoint. This is true for every trace we looked at. If we are concerned about the temperature of a trace, we probably want to estimate what that temperature is going to be. I'm proposing in this presentation that there are 5 ways to do that. The first, build a prototype and measure it. The second way is to look at experimental results and estimate what the temperature is going to be from that. For example, IPC 2152, the standard for determining current carrying capacity in printed circuit board designs, published by the IPC in 2009, is one of the best and most thorough studies of trace currents and temperatures ever conducted. This is a chart from that publication. It's for 2-ounce traces. It has the cross-sectional area in square millimeters in the horizontal axis, and it has the current down the trace in the vertical axis. So we look at the intersection between the cross-sectional area and the current, and then look at the temperature line closest to that intersection point. The good news is this will get us very close to what the temperature of the trace is going to be. The bad news is this applies to a specific set of parameters which may be different from the parameters on your particular board. And not all the parameters may have been reported in IPC 2152. For example, the resistivity of the trace and the thermal conductivity coefficients of the board material. A third method for estimating trace temperature is simulation, or mathematical modeling. This is a very powerful tool, and it gives us lots of outputs: graphs, thermal figures, numerical data that we can use for various analyses. It allows us to do sensitivity analyses. We can vary one parameter at a time and see how that impacts the temperature, and I will have more to say about that in a couple of slides. It is the single most powerful way that we can estimate what the trace temperatures are going to be. But it's still not perfect. For example, not all the parameters may be known, and the simulations are still estimates. Nevertheless, on the following slides, I'm going to give you just a taste of some of the things we can do with simulation. On this slide and the next, I'll show you a variety of different outputs we can get from a simulation analysis. On the left-hand set of curves, we have a set of curves that look a lot like an IPC 2152 output, just drawn on different axes. We can develop a set of curves just like the IPC 2152 curves, except they are customized for your particular manufacturing processes. The middle curve shows the length of time it takes for a trace temperature to stabilize. It is not instantaneous. There's a time constant associated with the heating of a trace. Simulation can give us this. The third graph shows us the relationship between the temperature of a trace on the surface and the same trace if it's internal in the board. This curve is showing that as a function of the depth of the trace in the board. These are just 3 graphical output examples that we can put together from a simulation. We can also generate a variety of images from a simulation. For example, on the top left, we have some horizontal thermal plots of the temperature along a trace. In the middle, we have a thermal plot of the temperature from the top of the board down through the board to the bottom of the board. On the right, we have a thermal plot of temperature associated with a via. This is an image of a trace layer on the top and bottom and the via in between. We can measure not only the temperature of the via on the top and bottom, but also the internal temperature of the via. We can do precise point measurements. This is an image of a heated pad, and we can measure the temperature on specific points on the pad. We can do adjacent trace analyses where we can put current down one trace and look at the impact on an adjacent trace. And then on the bottom left, we show that we can get some current density images. Now, these are really pretty and interesting images. They are totally irrelevant to anything that we might care about, but they are interesting nonetheless. And then there is still much, much more we can get from a simulation. A fourth way of estimating temperature is by the use of formulas. The formulas can be derived from theory, or from experimentation, or from simulation, and so on. Here we have a formula that we derived based on the IPC 2152 data, and this is in our book. A problem with formulas is that they are derived from a specific set of conditions or assumptions that may not apply to your particular process, and they may not include all the possible variables. But I did show you on a previous slide that using simulation, you can generate a set of curves that are specific to your set of manufacturing processes. If you have a set of curves like that, you can use regression analysis to develop your own internal formula that would be relevant for your processes. A fifth way of estimating temperature is by intuition. I will have more to say about that when we get to the section on vias. A simulation tool is particularly powerful for allowing us to do sensitivity analyses. For example, suppose we have a 100 mil wide trace, 1 ounce thick, 6 inches long on a 63 mil board, and we put 7 amps down the trace. Simulation tells us the trace temperature will be 56.7 degrees C. Now, let's vary the parameters individually and see how each one affects the temperature of the trace. And here is a summary of the results of our simulation. A detailed analysis of the simulation is included in Chapter 7 of our book. The temperature will change 1 degree for each 2% change in resistivity. The typical uncertainty of resistivity is 6%, so that can impact the temperature of about 3 degrees under the conditions of our simulation. The temperature will change 3 degrees for a 1/10 of a mil change in thickness. The typical uncertainty in thickness is maybe 1/2 mil. So that's a 15-degree uncertainty based on variations in trace thickness. The temperature will change 5 degrees for a change in the heat transfer coefficient between 11 and 14. Since we don't know enough about the heat transfer coefficient to begin with, there's not a lot more we can say about that. And the temperature will change 5.6 degrees for a change in the thermal conductivity coefficient of between 0.5 and 0.7. The typical range has been about 0.3 to 0.8, and it's getting wider as new materials are developed. So we can see that the thermal conductivity coefficient is one of the largest determinants of trace temperature. Variations in trace thickness would be the second most significant factor. Up until the time Johannes and I did our research, the conventional wisdom on via temperatures has been what is quoted here on this slide, and I'm going to read it to you. The cross-sectional area of a via should have at least the same cross-sectional area as the conductor, or be larger than the conductor coming into it. If the via has less cross-sectional area than the conductor, then multiple vias can be used to maintain the same cross-sectional area as the conductor. This is a direct quote from IPC 2152, page 26. And it turns out this conventional wisdom has been flat wrong. Now, I'm not criticizing IPC 2152 here. Almost everyone in the industry believed this conventional wisdom, and UltraCAD itself has written 3 or 4 articles in the past based on this conventional wisdom. Nevertheless, it turns out it has been flat wrong, and I will show you why on the next few slides. Here are the results of 2 simulations of traces with vias. One trace is 27 mils wide, the other is 100 mils wide, and each has a via connecting the top and bottom layer that has the same conducting cross-sectional area as the 27 mil wide trace. The 27 mil wide trace at a current of 3 amps has a temperature of 86.9 degrees centigrade. The top of the via is 81.4 degrees, the midpoint of the via is almost 81 degrees, and the via is cooler than the trace. Changing the trace width to 100 mils, but keeping the same size via, and putting 6 amps down that trace, the corresponding temperatures are 61.8 degrees for the trace, 77.6 degrees for the via top, and the same 77.6 degrees for the midpoint of the via. In this case, the via is a little bit hotter than the trace. Now, did you notice? Keeping the single via size constant between the 2 traces, 3 amps with a narrow trace got us a via temperature of almost 81 degrees, cooler than the trace. 6 amps with a wider trace got us a via temperature of only 77.6 degrees. That was cooler than with the 3 amps. 3 amps got us 80 degrees, 6 amps got us 77 degrees. I'm going to repeat the previous slide for you to look at again. The conclusion is that it is not the current that determines the via temperature. It's the trace. I'm going to say that again. It is not the current that determines the via temperature. It is the trace. The via temperature is not determined by the current through the via. As long as the trace is sized correctly, only a single via is needed, and it doesn't even need to be very big unless we are in an extreme design situation. Why can that be true? This is my attempt at drawing a scale model of a trace with a via. The typical board is only about 63 mils thick, and the length of the via is tiny compared to the trace. If the cross-sectional area of the via is the same as the cross-sectional conducting area of the trace, then the via looks like an internal trace. One of the things that IPC 2152 showed us is that internal traces are cooler than external traces. The via is similar to an internal trace, it cools more efficiently, and that's why the via is cooler than the trace. But if the conducting cross-sectional area of the trace is larger than the via, then the trace becomes a heat sink for the via. The via may want to be hotter than the trace, but it can't get much hotter than the trace before the trace pulls all the heat away from the via. Now think about a computer processor on a motherboard. The processor runs very hot, typically 35 to 85 watts. That's as big as a light bulb. But we keep the processor cool with a massive heatsink and a fan. If we didn't have the heatsink and the fan, the processor would melt fairly quickly. The trace becomes a heatsink for the via. The practical reality is the via can't get a lot hotter than the trace because the trace pulls all the heat away from the via. An important question is, how many vias do we need? The conventional wisdom says the number can be found by dividing the cross-sectional area of the trace by the conducting cross-sectional area of the via, and we get a quotient equal to n. The problem with that is that the current is going to split roughly equally between those n vias, and the power going through any particular via is I over n quantity squared times the resistance of the via. That means what we only need is the square root of n vias, not n from conventional wisdom. And the practical reality is we only need one or two less than that. The theory of that and some simulations will be found in a recent article in Printed Circuit Design and Fab, December 2023. Remember when I said that you could forecast with intuition? Well, we can guess that via temperatures will be between about the same temperature as the parent trace to about 10 to 12 degrees above the parent trace, depending on the relative size and temperature of that parent trace. Simulations are helpful in showing us why thermal vias don't work. Thermal vias, almost by definition, go somewhere. Typically, they go from a heated pad on the top of the board to a plane or a large pad on the opposite side of the board. The thermal vias transfer heat, supposedly, from the top to the bottom of the board. The conductive heat transfer formula, shown here, is the measure of heat that is transferred. Q over T is the rate of heat transfer in watts or joules per second. K is the thermal conductivity coefficient of the board material. Typically it's 0.5 for FR4. It's 385 for copper. A is the overlapping area between the heated pad on the top layer and whatever the via is connecting to on the bottom layer. Delta T is the change in temperature between the top layer and the bottom layer, which is also the change in temperature between the heated pad and the opposite side of the board. And D is the distance between the two surfaces, which is probably the thickness of the board. But here is a typical simulated image of the temperature difference between a top layer and a bottom layer. The lower image is an attempt to scale this, and it is clear that the board is really thin, so the temperature difference between the top layer and the bottom layer is not very great. In fact, the bottom layer of a board is typically only about 4 to 10 degrees cooler than the traces and pads above it, regardless of what is in between, including a plane. So looking again at the conductive heat transfer formula, what we have is a situation that delta T, the difference in temperature from the top layer to the bottom layer of this very thin board, delta T is very small. So the thermal via is ineffective. And what effect there is a point effect. The image shows a heated pad with 5 thermal vias connected to it. The temperature difference between the pad and the top of any thermal via is very small. In this image, it's less than about 2 degrees. And the thermal vias are only effective at a point. That's why people say you need a lot of thermal vias between a heated pad and the other side of the board. There is another myth I want to dispel in this presentation. Stop thinking in terms of current density. Current density is not related to anything, and it especially is not related to the temperature of a via. But it's not related to the temperature of a trace either. I'm going to demonstrate with 3 ways that current density is not related to anything, and we have more ways in our book. The first way relates to form factor. Here we have an image of a board with 3 traces on it. One trace is very narrow and tall. It is scaled at 5 millimeters wide and 0.099 millimeters tall. The second one is 0.75 millimeters wide and 0.066 millimeters tall. And the third one, C, is 15 millimeters wide and 0.033 millimeters tall. We're going to put 15 amps down each trace. Now the cross-sectional area of each trace is the same. It's 0.495 square millimeters. If we put the same current down the same cross-sectional area, we get the same current density, 30.3 amps per square millimeter. But the temperature is not the same on these traces. The narrow, tall trace has the highest temperature at 48 degrees. The wide, thin trace has the lowest temperature at 37 degrees. C has the lowest temperature because it has the largest surface area in contact with the thermally conductive board material. Form factor plays a major role in the temperature of a trace. The second way is by using the IPC charts. This is the same IPC chart I showed you earlier in the presentation. It has conducting cross-sectional area on the horizontal axis and current on the vertical axis. Therefore, any straight line drawn on this graph that originates at the origin has a constant current density. Every point along a straight line has the same current density. And yet, any straight line drawn on this graph crosses multiple temperature lines. This shows that the same current density has different temperatures depending on the conducting cross-sectional area of the trace. Or, stated another way, the current density will have different temperatures depending on the form factor of the trace. Finally, with apologies to those of you who don't like equations, I'm going to demonstrate the point using a little bit of basic algebra. Looking at the top line, the temperature of a trace is related to I squared R. We can rewrite that as I times R. And since R, the resistance, is equal to the resistivity, rho, times the length of the trace divided by the conducting cross-sectional area, we can finally get the expression the temperature of the trace is related to I times rho times L divided by A. On the second line, if we divide through by L, we get the temperature of a trace divided by L, which is the temperature per unit length, which is appropriate because temperature is a point concept at a point along the length of the trace. We get that the temperature per unit length of a trace is related to I times rho divided by area. If we collect the area term underneath the I term as shown here, what we also get then is the temperature per unit length is related to the quantity I over A times rho. Now, since the quantity I over A equals the current density by definition, which we refer to by the letter J, then what we end up with is that the temperature per unit length along a trace is related to the current density times I times rho. This is not a clean or pure equation in current density. It is an equation in current density times I, which is also a part of current density. It is not a clean equation, and therefore it shows that the temperature per unit length along a trace is not purely related to current density. The final topic I want to talk about in this presentation is fusing current. And here are two examples of where it might come into play. Suppose when I turn on my system, there's a trace that's going to carry 2 amps, but it's only going to carry it for 2.4 seconds. Then the current on the trace is going to settle down to a nominal amount. How big a trace do I need? In another application, if I have a dead short, a certain trace is going to carry 60 amps for just 150 milliseconds. Then the system is going to shut down in a controlled manner. How big a trace do I need? Up until now in our industry, when we've needed answers to questions like that, we've tended to turn to two people, W.H. Preece, who did his work in the 1880s, and I.M. Onderdonk, who we think did his or her work in the 1920s. We talk about these two people in Chapter 11. Each of these people is credited with developing an equation that relates how much current can go down a trace before the trace melts. Preece's equation on the left is relatively straightforward. It was derived experimentally in the 1880s, and he has written extensively on how he came up with that particular equation. I.M. Onderdonk's equation on the right is a little more complicated, but it includes the variable time. So he ostensibly not only shows how much current can go down a trace before the trace melts, but also how long it will take for the trace to melt. Onderdonck's equation is derived theoretically, and it explicitly assumes that there is no cooling. Dr. Adam, in a very good piece of work, has rigorously derived Onderdonck's equation in Appendix G. These two curves are the result of two simulations of fusing current down a trace. The horizontal axis is the amount of current that goes down the trace. The vertical axis is the time it takes for the trace to reach the melting temperature. The blue line models an actual trace on FR4 board material. The black line is Onderdonck's equation, assuming no cooling whatsoever. When these traces start out on the far right-hand corner of the axes, the curves are approximately the same. At 75 or 80 amps, each one takes under a second. In fact, under a half a second. But as the current goes down, it takes longer for the trace to melt. For example, at 20 amps, the Onderdonck equation predicts a trace will melt in 1.5 seconds. But an actual trace on a board might not ever reach the melting temperature. These two curves show the difference that the no cooling assumption makes in a model. We have much more to say about fusing temperatures in Chapter 12. Here are two images showing the moment that a trace fuses or melts. On the left, what we see is a little bright spot that is one frame in a video, 1/30th of a second. There is nothing on the frame before, there is nothing on the frame afterwards. It's just this little tiny spot. But on the right, the situation is dramatically different. Here, the trace has become very hot all the way along its length, burning the board material underneath it. There is a lot of smoking coming up from the board material, and in one spot visible in this frame, there is smoke being ejected out from under the trace toward the bottom left corner of the image. And when the trace melted, it did so in a very bright flash of flame. We will leave it for you to go look in Chapter 12 at what the difference is between these two situations. This research project could not have been done without the help of many others. Some of them are listed here, and in particular, we want to acknowledge Prototron Circuits, who at the time had an office in Redmond, Washington, and Prototron supplied many of the test boards that we used. There is a lot more in our book. We hope you buy the book. Thanks for watching. That's it for now.